Hello everyone, welcome to the kinematics and dynamics of machinery class. In this video we're going to continue the topic that we started in the previous video, which is the dynamic analysis of force analysis of mechanisms. And in this video I'm just going to explain the general procedure of how we can do dynamic force analysis of the mechanism. Then I'm going to show you an example. I'm going to solve an example on this topic. Just a quick reminder of the thing that we already covered in the previous video. We give like a little bit introduction about this topic and what does it mean, what is the difference between static force analysis and the dynamic force analysis. Also, we discussed different important cases that we would experience when we consider the force analysis of different mechanisms. Like the case, we may have a member or a link that is subjected to two forces at the ends. We give it a name like two force member. Also, we discussed how we can do force analysis to a three force member. Also, we consider the general case in case that we do have like a member that is subjected to some forces, like two forces at the ends, in addition multiple forces and even a torque that would be located in the middle between these two ends acting on the member. And we discuss how we can handle and deal with this type of member. Also, we discuss the case that you do have two force and couple member, like two forces at the ends and one couple in the middle, and we said that this is gonna be for this case that the two forces at the end will be parallel and of the same magnitude but of the opposite directions, and there should be a normal distance between them. This normal distance depends on the torque that already generated or acting on the member. So this very quick, the thing that we already discussed before. Again, the objective is just to show you the general procedure in addition to give an example on these things that we already covered so far. But before doing so, let us fix some points regarding the reactions at pairs. We said that the joints between the different lengths of a mechanism, these are the base, and this is the first topic that we already started in this course. We discussed this one in the second lecture of this class. So to explain these different reactions, and this is one of the requirements basically of any type of problem, like it will be required to come up or find the reactions at the these reactions at the different pairs of the joints between the different lengths of a mechanism. So to explain it, let us consider this slider crank mechanism. This is one of the simplest mechanisms that we already covered through this course. Like this is the joint and this is gonna be the crank, and you're gonna have here the connecting rod or link, and then definitely we're gonna have the slider. Let us just draw this horizontal line, making sure that the slider is already located. This is gonna be the slider that slides over the ground, and we're gonna have here the connecting link which doing general motion. And we would give some names to these points like A, B, and C. And this definitely is gonna be the first link. As we usual, this is the ground, which is link 1, and we're gonna have link 2 in addition to link 3. So for this slider crank mechanism, if we decided to work as force analysis, we have to break it down. Even we used to do so from the static class. Even if we do have a mechanism, this mechanism entirely, it will be in a static or under dynamic equilibrium. But in many of the cases, the number of unknowns, it will be more than 3. As long as we're already working in 2 dimensions, we are limited for just 3 equations, that the sum of forces along x, one equilibrium along x, one equilibrium along y in terms of forces, in addition to the moment equilibrium at any point that belongs to this mechanism. So, but especially if we're already interested in finding the reactions at the point B and point A and point C, there should be some reaction forces here. The same thing, some reaction forces at these points. These points, these are the pairs as we define them in the beginning of this class. So if we are interested in finding the reactions at these pairs or the forces that already generated at these pairs, and this is what we're going to do to have a complete force analysis, is just to find these reactions. These reactions, to show up, we have to split it. We have to like separate these lengths from each other. Like we have to break it down or divide it into multiple lengths, and we have to deal with each one of these lengths separately. to have these reaction forces to show up. But as long as these links already assembled together, there is no reactions will be apparent in this case. Like the resultant reaction force here, it will be zero, because there should be reaction coming from this link and there is another reaction that is coming from the other link. These two reactions from the two different links, they are equal in terms of magnitude, but of opposite directions. So that's why the apparent force, the external force here, the apparent force at point B, it is zero. The same thing applied at A and C. But these forces will show up as long as we're going to deal with these links separately, and this is what we're going to do. So if we break it down into multiple links and we consider the discretization of this mechanism into multiple links, so we should have here one link, which is link 2, and we definitely going to have another link in addition to the slider. So these are the three components that form this mechanism. It has link 1 and link 2 and link 3. The frame is just fixed link. This is the ground, and the third element definitely is going to be the slider, and this is the point C, and definitely this is going to be point C as well. This is going to be point B, and this is also point B for the link 2, and this is point A. Make sense? So, and even we can give it a name like this is link 2, this is link 3, and this is the slider, which is number 4, as we used to give it a number like any other element within the mechanism. And definitely you should understand that this link is already moving, or this slider is already sliding over the ground. Now, how about the reactions? First of all, at this point there should be reaction, but this point A, it is a common point between two links or two frames within this mechanism. One is the frame, which is the fixed link, which is link 1 and link 2. So what does it mean? It means that there should be a force. There should be a force at A. This force at A is going to be the force that is already coming from link 1 acting on link 2, as long as we're already working over link 2. Now, if we already working over link 2, trying to do force analysis to the link 2 or to the member 2. So it means that we are interested in finding the force that acting at point A that bring to point 2 coming from link 1. Why? Because point A, it is a common link point between the two links, between 1 and 2. So this is the force that comes from 1 acting on 2. How about B? B, it is a common point between two links, 3 and 4. So there should be a reaction force here, which is F, that comes from 3 acting on 2, because we're already working over the link number 2. And since we're already doing this wavy thing at these points, this indicates that this force is unknown in terms of magnitude and direction. We have no clue how much is the magnitude, how much is the direction of these 2 points, or of these 2 forces. How about this point B that belongs to the link number 3? If you remember from the statics or even the dynamic class, like this reaction force that is already generated at point B due to the assembling of these 2 links, this force, it should be the same, whatever it is going to be counted or calculated from link 2 or link 3 in terms of magnitude, but they're going to be of 2 opposite directions. So the reaction at point B, it should be the force that comes from 2 acting on 3. The same thing, the force here, it should be the force, because here is a common between link 3 and 4. The buoyancy, it is a common between link 3 and 4. So this should be the force that comes from 4 but acting on 3. Make sense? Something that you should understand about these 2 forces, because this is the common point, this is the same point, that these 2 forces, they should be equal in terms of magnitude. It means that the magnitude of F32, it should equal to the magnitude of F23, but their directions are, but these 2 forces are of 2 opposite directions. This is something that you should understand about these 2 forces. So you should understand that the force F32 vector, it should equal to the negative of F32 vector. This negative indicates that it is opposite direction but of the same magnitude. Make sense? The same thing here. For example, if we consider even the ground, we should have like kind of ground here. So this force, there is a force that comes from the link 2 acting on the ground. It means that there should be another force. As long as we don't have F12 vector, there should be F21 vector. F21, this is the force that comes from the link acting on the ground. If you are interested in doing or finding the reaction acting on the ground itself, but basically this is, we are not interested in such a thing, and instead we are interested in finding or doing force analysis to the mechanism itself. But this is something that you should understand also, that if we switch this this indicate that we already talking about the observe or the opposite to this force in terms of direction, but still having the same magnitude. The same thing applies here. So this is point C. You should understand that this point as well that belongs to the link to the slider, it is also point C. So this point C is a common point. So it means that at this point C, there should be another force. And again, that this force, we have no clue how much is its direction or magnitude. So this force, it should be the F3-4. This is the force that comes from 3 acting on 4 because we're already working over the slider number 4. In the meanwhile, the slider is already in contact with the ground and there should be contact force. There should be pressure. There should be force as an action force. Even if you remember from the static class or the dynamic class, we said that any object that is already sitting on the ground, there should be a normal force generating between this object and the ground, right? So this slider is already sliding over a surface, whatever it is, horizontal, vertical, inclined, even if it is a curved surface, there should be a normal force. There should be a reaction acting between, comes from the ground acting on the slider. So there should be a force here. And the direction of this force all the time, it should be perpendicular to the surface as we did in the dynamic class, if you remember. Like this direction of the force, all the time it is perpendicular to the surface over which the slider is already moving. But we cannot decide whether it is going up or going down. This, we're gonna keep this thing till the end. As we discussed in the previous video, if you already knew the line of action of the force, this indicates or this means that you already have the direction of the force. But we are not sure what is the exact direction. Is it going up or down? Initially, we're just going to assume that this is the line of action and that's enough for us to move and to do force analysis. Make sense? So it means that this force, which is the force that comes from the ground, which is 1, acting on 4, because we're already working on 4. So this F14, it should be perpendicular. We knew its direction. It's gonna be, its direction will be given, but its value will be unknown. But the other forces, all of them will be initially unknown, and the objective is just to find them. And this is the objective of the force analysis that we are going to do for such a mechanism like this one. Make sense? So this is how we can define the reactions of the pair at the different joints and different pairs. And this is an important thing. This is one of the things that we're gonna do during the force analysis procedure. Something also that you should understand about F14, like this force which is already coming from the ground acting on the slider, it should be perpendicular to the surface over which the slider is already moving. Another thing, if you decided, if we are interested in defining the pressure or the pushing of the slider over the ground, it means that we are interested in F41. F41, it should equal to the F14 with the same magnitude but two opposite directions. Make sense? So this is the thing that we should understand about the reactions. Also, there is a very important case here that we shall consider, which in case that we do have a link, like a slider slides over a link. Slider that slides over a link like this case. So for this case, this slider, there should be a pair, there should be a contact surface, there should be like kind of pressure acting between the slider or the slider on the link and the link on the slider. So if we just give numbers, let us assume that this is like link 2 and this is slider number 3. And let us assume that this point, which it should be the common point between them, this is like point A. So if we decided to do work analysis, we have to work separately for each one. Like we're gonna deal with the link separate from the slider. So this is gonna be the link and this is gonna be like the point A that we're already talking about, and we're gonna have the same point A that belongs to the link itself. You should understand that this should be a force. This is, here we are talking about the link 2 and this is slider 3, so there should be a force coming from 3 acting on 2, and the direction of this force, it's gonna be perpendicular. It's gonna be perpendicular to the link. Why? Because this is the line of action. This is the sliding motion. The slider is going to slide over this surface. So the normal force, it should be perpendicular to the direction of motion of the slider as we did for this slider here. So this force, this is the direction of the force will be known, but where exactly, is it going down or up? We don't know. But To us, this direction is already known, and this force, this is the force that comes from 3 acting on 2. The same force, it should be acting on the slider. The same force with the same parallel direction, but opposite. The same parallel direction, but opposite direction. And this force is going to be the F23, which comes from 2 acting on the slider number 3. So these two forces will be given, their directions will be known. We can decide their directions, but their magnitudes in many of the cases will be unknown. And this is what we have to do in terms of the force analysis. So this is also one of the things that we have to consider when we do force analysis and start to generate these reaction forces at the different pairs of the mechanism. Make sense? Now let us discuss the general procedure that we're gonna apply to do dynamic force analysis of a mechanism. So these are the general steps. This is the general procedure. Basically, we should start with making a complete kinematic analysis of the mechanism before we start doing dynamic analysis or the kinetics. As we even used to do from the dynamic class, we have to finish the kinematics first, then we can move to the kinetics. The kinetics should come after the kinematics. It means that if you're already given a mechanism, we have to finish first we have to do a complete kinematic analysis of the mechanism by finding all the positions, the velocities and acceleration of all the mechanisms entirely. Once we finish that, we can move to the force analysis or the dynamic force analysis part. But we weren't gonna able to proceed to the kinetics or the dynamic analysis or force analysis unless we finish this part first. So this indicates that if I decided to give you a problem with a mechanism and you have to finish all the kinematics analysis, then you're gonna move to the force analysis. It is a long process, as long as we're already using by hand, but now there are some software that we can do these things very quick. But anyway, in many of the cases, I'm gonna give you all the details that you need for the force analysis from the kinematic analysis. So it means that you will not be required to do the kinematic analysis part, and any data or information that you need for the force analysis, it will be provided or given to you in the example or the problem as I'm gonna show you now. Okay, but there is another thing, because you already have a project, so you have to do this thing in your project. Like you have to finish the kinematic analysis part, then you're gonna move to the force analysis part. So what is the thing that you need from the kinematics to proceed to the force analysis? Or what are the data that you need from the kinematics analysis to do force analysis of the same mechanism? The main thing, basically, you need the acceleration terms. We don't need the position, we don't need definitely the position, we're gonna use it, but I'm talking about the essential things. We don't need the velocities, but we need the acceleration component. The acceleration of the different lengths, especially the angular accelerations if we have a length that rotates. In addition, if we have a slider that moves, we need its acceleration. Plus, we need the acceleration of the center of gravity point, the point of the center of gravity of all the lengths. If we have a length that rotates or even moves, any object, whatever it is, any membrane that belongs to the link, we have to specify its mass center point, where it is, and we have to find the acceleration of this point. This should be done during the kinematic analysis part. So as I said, in many of the cases, I'm gonna provide this data. I'm gonna give you the acceleration of this mass center points. In addition to, I'm gonna give you the angular acceleration for any length that already basically rotate. And these are the things that we need from the kinematic analysis part, right? As already given here or written here in this notice. Also, once we do have this data, especially the acceleration things for the mechanism, we can use these acceleration terms to calculate the inertia forces and the inertia moment for the different lengths and different components or elements of the mechanism. Like the slider crank mechanism, this mechanism consists of 3 main elements. So your objective is just to calculate for each individual element, for length 2, for length 3, and the slider. You have to calculate for each one how much is the inertia force, how much is the inertia moment or torque in case that this object is already rotating. Like for example, this length 2 is going to rotate, so it has an inertia force plus inertia moment. Inertia force, because its mass center, especially if its mass center, for example, assume that this length, its mass center is already located here. So this is like G for link 2, and this is like the G point. This is the center point, but for link number 3. and assume that this point is G for object number or element number 4, which is the slider itself. Assume that this G points already given to us, this center point's already given to us. So as long as this link is moving or rotating, this point G is moving, so it has acceleration, and it means that there should be inertia force generated at this point G. So there should be one inertia force in the direction of the acceleration and opposite to it. So there should be like VI, Fi for link 2. This is one inertia force. Also, because this link is already rotating, so there should be an inertia torque acting over this link number 2 because of its rotation. But for some reason, if this link rotates about its mass center point, it means that this point G2 has zero acceleration, so there is no force, but there is still moment. The moment will be still there. Why? Because there is rotation. As long as there is angular acceleration for this link, and this link, its mass is significant to be considered, or to consider its inertia force or inertia moment. The same thing applies for the third length. Length 3, it will have some force, like F inertia 3. We have to calculate this thing in the second step that I'm talking about in the procedure of the dynamic force analysis. Plus, we have to calculate the TI3, which is the inertia torque or moment for this link. How about the slider? The slider is not rotating, it's just moving. So it will have only one inertia force in its direction of motion as Fi4, and there is no torque or moment in this way. So this is the objective of the second step. The objective of the second step is just to come up or calculate these inertia forces and inertia moments for any length that rotate or move depending on its type of motion. If there is any rotation, so there should be inertia moment. If there is no rotation, there should be only inertia force. Generally speaking, the inertia force, its magnitude, you're gonna calculate the magnitude of the inertia force. It should equal to the mass times the acceleration of the mass center of this member. And this is gonna be the magnitude of the acceleration. The acceleration magnitude will be given to us, or if it is not given, we have to finish the kinematic analysis part, and we come up with a value for this EG, multiply times the mass of the link, as long as the link with a significant mass, and substitute, you're gonna end up with the inertia force. Also, the inertia torque or moment, which is T inertia, is gonna be the I times the acceleration, which is the magnitude of the acceleration vector or the angular acceleration of the link, which is gonna be the I, which is the mass moment of inertia about the mass center G. You should understand that this I, this is the mass moment of inertia, mass moment of inertia about the mass center G of the link, and it will be given. This mass moment of inertia will be given. Definitely the mass of the member also will be given. And as I mentioned, in many of the cases, this EG and alpha will be given, so we can simply calculate these inertia forces and moments, and this is the second step. Then the third step, you're gonna work on combining the inertia forces and the inertia torque and any other forces into one force acting on the member. Like for example, like this mechanism, like the slider crank mechanism, like for example, link number 3. How many forces do we have for this link number 3? We do have 3 forces. We do have the torque. We do have 2 main forces in the middle. We do have the torque, which is the inertia torque, plus the force. And probably for some reason we may have some external force. So we may have like F external, like this is kind of external force. So in total, we do have like 2 forces or more than 2 forces even acting in the middle of a link, plus some moment. Your objective is just to combine them as we explained before for the general member case, as we explained in the previous video. So this is going to be the third step, is just to combine any forces or moments acting on any specific link into just one force. Makes sense? And especially for this case, it is recommended to skip the external force, and or even you can add the external force. It's gonna be clear as we more proceed or we consider the example. But anyway, your objective is just to combine all of these forces into one equivalent force over this link. The same thing here, we have 2 forces, so we're gonna combine them into one equivalent force, and so on. This is gonna be the third step. And once we do this third step, till now we didn't do any force analysis, by the way. We're just preparing for the graphical. Remember that we're gonna do all these things graphically. Then once we combine these forces together over each individual link, we can move to the force analysis. And to do the force analysis, we're gonna use a principle which is known as the superposition principle to do the dynamic force analysis. There should be here force analysis of the different members of the mechanism, and this is what we're gonna explain. So what does it mean, the superposition principle here? Like, for example, if we have a mechanism, let us assume this simple mechanism as 4-bar linkage. Like we do have, this is the first link, which is the ground, and we do have another link and the third link and so on. So these are like 4 links, 4-bar linkage in this case, and assume for some reason there should be a force acting on this link, F3, and there is another force acting over this link as F4. Like this is link 1, this link 1, which is the ground, and link 2, and link 3, and link 4. So to do force analysis, we have to separate the links. We're gonna deal with every link individual. And for that case, when we separate the links, we're gonna end up with some reactions will start to show up at the 2 ends of each link. Make sense? But the entire mechanism, it is subjected to 2 forces. It is subjected to 2 forces. So what is the concept of the superposition principle? Like if we consider this force F3, this force is already acting on the link number 3, but it has an effect on the other links in terms of the reaction that shall be generated at these different points of the mechanism. The same thing applies for force F4. F4, it directly acts on the link number 4, but in the meanwhile it do have indirect effect on the other links that belong to the mechanism. So to do force analysis for this mechanism, we're gonna assume initially that we're gonna have the same mechanism in this way, but it is subjected to only one of these 2 forces. Like initially in the beginning, we're gonna assume that it is subjected to F3 only, and F4 is gonna be 0. Then we're gonna do analysis to this mechanism, and we find all the reactions at these different joints, at these different pairs. So this is gonna give us, like, for example, like this pair at this joint, we're gonna have here some reaction forces like the F2,3 and the F3,2, right? Dash and dash. So this is gonna be from the first run, from the first case, right? Assuming that these are the reactions that generate over this mechanism because of one force, which is F3. Plus, then we're gonna repeat again. We're gonna repeat the same thing for the other mechanism, for the mechanism one more time by subjecting the mechanism into the other force. Now we're just gonna assume that this force, F4, it will be with a value. We're just gonna apply F4, but we're just gonna consider F3 equals 0. So it means that we're just gonna break down the problem into like 2 different problems. This is the superposition principle, and then we're gonna repeat again and repeat the process to come up with F2,3 double dash and F3,2 double dash. These are the reactions for the second case. And definitely we're gonna find all the other reactions. It is not just these 2 reactions at this joint or this pair, we're gonna do it for all the joints. Then once we find these reactions at these 2 different, for these 2 different scenarios, we're gonna combine F2,3 dash with the F2,3 double dash to come up with the resultant of them at the entire or the total reaction force at this pair or this joint. So this is how it works. Like instead of finding or working, because if we decided to work at once, the number of unknowns will be more than we are expecting. And remember that we are limited for just 3 unknowns to be able to do force analysis graphically using for this part. So we are limited for just 3 unknowns. These unknowns will be 2 directions of 2 different forces plus 1 magnitude of 1 force. To do so, we have to separate the forces. We have to work using the superposition principle, and this is very quick. What does it mean, this principle? And it's gonna be clear as we move or we consider the next example. Make sense? So this is for the general procedure, and as you can see, all the previous three steps that we initiate, we start the process. And the physical force analysis part is going to be the fourth step using the superposition principle. And this is going to be very clear when we consider the next example. Make sense? So let us consider this example of the 4-bar linkage. This is the crank, which is link number 2, and it is connected between O2 and B. And this is another link, which is BC, which is link number 3, that doing general motion, in addition to this link number 4, which is also doing rotation about point O4, that is already set up between O4 and C. And these G2, you're going to find G2, G3, and G4. These are the mass center points of these different links or members. Like this member number 2, its mass center point, it is already G2. G2 is conceded to point O2 as already given here, and as already given in this figure, while point G3 is already located somewhere between points BC, between the 2 points BC over the link number 3. The same thing for point G4, it is located somewhere over the link, but G2 is considered to point O2 for the link number 2. These are the specification for this link in terms of the geometry, and this angle is theta 2. Definitely theta 2, it should be given somewhere. It is already given by 130 is already given down here. This is theta 2, and omega 2, which is the angular velocity for the crank, is already given by 95 radian per second, and it is constant. So this indicates that alpha 2 definitely is going to be 0 for the crank number 2. And the crank, as we discussed before, this crank is this something that is going to give motion to this mechanism. Like initially or generally, the motion for this type of mechanism, the motion starts from this crank. Like once we can fix a motor, we can put a motor here to give rotation to this crank. So this motor, once it rotates, it's gonna give rotation to the entire mechanism. Like this is like a single degree of freedom mechanism that require only one input to give rotation to the entire mechanism, as we discussed before. And there are lots of data that already given regarding the mass of the different links, in addition to the acceleration of these different points. Remember that, as we discussed, the thing that you need from the kinematic analysis is the acceleration of the center points of the links in addition to their angular acceleration. This is what we need from the kinematic analysis. We don't need any other thing. We don't need any information regarding the velocities except the acceleration things. The mass of link number 2 is already given by 0.1 kilogram. This is the mass of link number 3, 0.2 kilogram, mass of link number 4. In addition to the mass moment of inertia, which is Ig2, Ig3, Ig4, these are the mass moment of inertias of the three links as already given by 20 kilogram millimeter square. So I'm converting here, multiply times 10 to the power negative 6 to convert millimeter square to meter square. The same thing for 400 kilogram millimeter square, I converted it into meter square, and so on. So try to stick to this dimension, like any mass should be in kilogram, any dimension is going to be in meter, or all the dimensions. Try to achieve uniformity in the dimensions, whatever, making all the dimensions in terms of meter or all the dimensions in terms of millimeters, it's up to you. So I decided to work with the meter, so that's why I converted this millimeters into meter square. And it is required using the superposition principle to make a complete dynamic force analysis to come up with all the reactions acting on all bearings. How many bearings? Would have one bearing at O2 and another bearing at B and another bearing at C. In addition, there is O4 bearing. So it is required to find all the reaction forces at these 4 different bearings. And also it is required to calculate the torque required to drive the crank. This crank, as we mentioned, there should be like a motor set up here. So this motor should provide a sufficient amount of torque to give rotation to the crank. Of the torque that the motor generates, it is not big enough to give rotation to the crank. The mechanism won't gonna be able to move, and we're gonna end up with problems with this mechanism. So how much of torque that is needed to give rotation to this or to move this mechanism, this is what we are required also to calculate for this mechanism. And this is going to be the last step. The last thing to do is just to find this torque. And there are some other things that already related to the geometry of this mechanism, like the distance O2, O4 already given by 70 millimeter, the BC, the OC, all the geometry of the mechanism, even the locations of the center points of the CG point, DG2, G3, G4. G2 it is automatically over O2, but G3 is already located such a way that BG3 is already given here by 50 millimeter, and O4 G4 is already given by 25 millimeter. It means that this distance from O4 to G4 is already given by 25 millimeter. So all these data are given in addition to the theta 2, in addition to the angular velocity of the crank number 2, and this is the information that is already given in addition to the acceleration of the link. Definitely is going to be alpha 2 is going to be 0. Plus, in addition to this, the acceleration AG3, which is the acceleration of point G3, is already given by this value, and this is its direction. So this is the value, the magnitude of the acceleration, plus this is the direction, and it is given in millimeter per second square. You can convert it into meter per second square. It's up to you. And there's going to be 100,000 for EG4, the point G4, and this is its direction is negative 52. Negative 52, it means that instead of going counterclockwise direction, we're going to go clockwise direction, as I'm going to show you how we can specify or identify the direction of these accelerations. Also, the angular acceleration alpha 3 of the link number 3 is given by 520 second per second to the power negative 2. This is indicate radian per second square, which is its direction counterclockwise direction, but alpha 4 it is 2740 second radian per second square, and its direction it is clockwise. And this theta 3 and theta 4, these are the angles already given in order to regenerate the geometry of this mechanism. So all of this information were provided to us. Most of these calculations or most of this information related to the position, the kinematic analysis part. So it means that you're gonna skip doing the first step, which is the kinematic analysis, and you're gonna directly go to the force analysis. But before that, we have to prepare, which is step 2 and step 3. Step 2, if you remember in the procedure that we explained on the top, that step 2 is just to find or to calculate the inertia forces and torques and moments that acting over the different links. We do have 3 links. The ground will be skipped. We won't gonna do anything regarding the ground. Now we're gonna move to the first step. So the first step here is step 1 is just to calculate. So remember, step 1 is to do kinematic analysis, but we're gonna skip this step. So now we're just gonna move to the calculation, calculate force and moment inertia. So we said that generally the inertia force, the magnitude of the inertia force, it should equal to the mass times the acceleration of the mass center, the magnitude of the acceleration, and the inertia torque, it should equal to the IG, which is the mass moment of inertia of the length times the magnitude of its alpha, or the magnitude of its angular acceleration. Make sense? So we're gonna use these two expressions, and we're gonna calculate for length 2. We do have 3 lengths. We're gonna do the calculation for length 2, length 3, and length 4. As already given on the top here, we do have length 2, 3, and 4. For length 2, to calculate the inertia force, we need the mass. The mass of length 2 is given by 0.1 kilograms, and we need the acceleration, which is already given here, but we have to convert this millimeter into meter. But we're gonna pick the magnitude for now, just the magnitude, which is 235,000. This is gonna give us the acceleration. So the inertia force, Fi for length 2, the inertia force for length 2 should equal to the mass of length 2 times the acceleration Eg2. So how much is the mass? M2 is already given by 0.1 kilograms, but how about the Ag2? Ag2, if you can read through, he didn't give us the acceleration of buoyant G2, how much it is. And by the way, the acceleration of buoyant G2, it should be 0. Why it should be 0? Because definitely this buoyant G2 is considered to point O2, and O2 it is a fixed point. It means that it has no acceleration. So Although he didn't give us the acceleration, but intuitively this acceleration term it should be 0. So this is gonna give us 0. Why? Because the AG equals 0. So this is for the FI2. How about the TI2, the inertia of the link number 2? It should equal to the IG2 times alpha 2. Alpha 2 also is 0 because he gave us that the link 2 rotates with a constant angular acceleration of 95 radian per second, so it should be constant. It means that alpha 2 is going to be 0, so that's why this inertia term as well is going to be 0. This is for link 2. We're going to repeat the same thing but for link 3, starting with the inertia force for link 3, which it should equal to the mass m3 times the acceleration ag3 equals the mass of link 3 is given by 0.2 kilograms times the acceleration ag3, which is already given to us here. This is ag3 235,000, and this is the magnitude, and it is in millimeter per second square. So I have to convert it into meter square to end up with the force in terms of Newton. So this is going to be the 0.2 kilograms times the 235,000 divided by 1000 to convert from millimeter into meter square. We're gonna a meter per second square. This is gonna give us the inertia force number 3 will be definitely equal the 47 Newton. Then once we calculate the inertia force 3, we can calculate the inertia torque for length 3, which it should be the IG3 times the alpha 3. Alpha 3, IG3, they should be provided to us, already given to us. IG3 is given by 400 kilogram times millimeter square. I converted into meter square by multiplying times 10 to the power negative 6. This is for IG3. And the alpha 3 is already given by 520. And I don't care about the direction, I'm just calculating the value. So this value, it will be 400 times 10 to the power negative 6 times the 520. And doing the calculations, we're gonna end up with 0.208 Newton times meter. This is the unit for the torque. For a link that has a torque and force, calculate for this link H, and we're gonna give it H3. This H3, as we discussed for the two force and a couple member. Like in case that would have a member with a force and a torque, and we would like to combine both of them together into one force, we have to calculate H, right? This H should equal to the torque divided by the inertia force, or divided by the force. So we're gonna calculate this H3, which is gonna be the inertia force number 3 divided of length 3 divided by its inertia, the inertia moment divided by the inertia force. Doing the calculations, we're gonna end up with 4.425 times the 10 to the power negative 3 meter. If we decided to convert it into millimeter, so it's gonna be just 4.425 millimeter. This is gonna give us the H3. And this value of the H3, we're gonna use it for the drawing as I'm gonna show you. Then we're gonna repeat the same thing for link 4. So as long as we have a torque and a force, as inertia, calculate automatically the H that corresponds for this one. Now let us calculate if I4, which is the inertia force for link 4, it should equal to the mass 4 times the acceleration EG4. The mass 4, which is already given on the top here by 0.3, and the acceleration is given by 100,000 acceleration. So this is gonna give us the 0.3 times the 100,000 divided by 1000 to convert to meter per second square. And doing the calculations, we're gonna end up with 30 Newton. This is gonna be the inertia force, and the inertia torque for link 4 is gonna be the IG4 times the alpha 4. IG4 was given to us by 100 times 10 to the power negative 6 to convert from millimeter square to meter square, times the acceleration alpha 4 was given by 2,400 and 740, and doing the calculation, this is gonna give us 274 Newton times meter. Since we have a torque and a force, we're gonna calculate H, which it should be the TI4 divided by the FI4, the torque divided by the force. This is gonna give us 9.133 times 10 to the power negative 3 meter, which can be converted into millimeter as 9 millimeter 0.113. or 133. Make sense? So this is the second step in the general procedure, but since we already skipped the initial step, which is the kinematics, because all the kinematics that are already given to us, we move directly to the calculation of the force and the moment, and this is gonna be the second step. The third step is just to try to combine these forces together into one force. But we're gonna do this combining thing when we start to draw the mechanism itself. And this is gonna be the second step, you could say. Like the next step that what we're gonna do right now, we're just gonna set up some scale, drawing scale to the mechanism, and we're gonna start drawing the mechanism to scale as already given to us. Then over this mechanism, we're gonna define, we're gonna put or identify the directions of all of these different torques and forces, then we're gonna combine them. So it means that you should have a separate sheet as drawing sheet. Over this drawing sheet, you're gonna start to draw the mechanism and both these forces to combine them. So now let us move to the drawing sheet. You have to make sure that you're gonna use one drawing sheet, A41, white page, and all the drawings of all the force analysis, it should be done over one sheet. So try to be like efficient in using the spaces and the areas within this drawing sheet, because definitely we're gonna have lots of drawings as I'm gonna show you. So the first step, as we discussed, that we should do the kinematics analysis, but all the data already given. And the second step is just to calculate the inertia force and the inertia torque in addition to the H value. And you have to do all of these calculations for all the elements that we do have in the mechanism. In this mechanism, we do have 4 bar linkage. It means that we're just gonna have 3 links which or 3 members that we have to do analysis for. And then the next step is just to draw the mechanism as already given to scale. So the dimensions in the mechanism, so I'm just gonna have a copy of the mechanism here because we're gonna use it for drawing this mechanism. And remember that this copy shouldn't be there. So I'm just have this one to have a reference, as a reference, so we can draw the mechanism up there on the top. But as I mentioned, that all of these dimensions like O2, B, the distance BC, all of these distances and dimensions and angles should be given to us, and it is already given to us in the main problem text. So we're gonna start here and try to generate this mechanism to scale within this top area. So having a look to the dimensions that we already have here the O2B. The O2B, this distance, it is already given to us by 30 millimeter, and the BC is already given by 100 millimeter, and the O4C is already given to us by 50 millimeter. So given these dimensions, we have 30 millimeters, 50 millimeters, and 100 millimeter. And the distance even O2, O4 is already given by 70 millimeters. So you can assume a scale 1-to-1 to generate this drawing or this curve, or you can scale it up or scale it down, it's up to you. But for these dimensions as already given to us, scale 1-to-1 is much more efficient or much more enough. So what I'm gonna do, I'm just gonna try to have this line, and I'm gonna draw above this line, I'm gonna draw the mechanism. So we're gonna start as we did many times before, even for the position analysis. I'm gonna start from any point. This is gonna be like assuming that this is the point O2. So this is the start point that I already have O2, which remember that as he as he already gave us in the problem that G2 is already considered to point O2. Then from this point we're gonna draw a horizontal line. So initially we're just gonna draw any light line, very light line in this way, and over this line we're gonna measure the distance O2, O4, which is already given by 70 millimeter in the main problem. So 70 millimeter, it means that you're just gonna measure 77 centimeters starting from the O2 point. Then you're gonna mark another point to locate the point O4. Then you're just gonna draw the support and just connect these 2 points together. We're gonna end up with the first link. Then what, you just gonna measure the angle theta2. Theta2 angle is already given, which is this angle down there. It is already given to us by 135. So you're gonna use the protractor and fixing from this point, you're just gonna measure an angle in this direction with 135. Then you're gonna mark a point on the top somewhere here. Then you're gonna connect this point, this center point to this point to draw a very light line in the beginning. So we can use even a different color here for this line. You're just gonna draw a very light line that is barely seen. Then over this line, you're just gonna measure the O2B, which is already given by 30 millimeter. It means that you're just gonna measure 3 centimeters and you're gonna mark a point. So we're gonna measure 3 centimeters and mark a point here. Then your objective is just to connect these 2 points together with a line. You're gonna set up the second link. This is gonna give us the link number 2. Make sense? Then you're gonna do the same. We would like to locate point C. So how we can locate this point C? He gave us all the angles. Theta 3 is already given, theta 4 is already given, but even if theta 3 or theta 4 were not given as already in the mechanism, we can identify or locate point C as we did in the position analysis, typically the same way. Like you're gonna use the compass fix at point B, then you're gonna draw one arc with radius 100, which is BC. Then you're gonna fix at O4 and open the compass with the O4C, which is 50 millimeter, and you're gonna draw another arc. This is gonna give us a locus. Then you're gonna end up with this point C. Or simply he gave us even the theta 3 and the theta 4. So your objective is you have to the either options. You can even use this angle that is already given to us, which theta 3. It means that starting from point B, this is gonna give us point B. From this point B, you're just gonna draw a very light line, horizontal line. Then you're gonna measure this line. Then you're gonna measure the angle theta 3, which is already given by 17 degrees. Then you're gonna draw a line with a length 100 millimeter, or you can do the same using the compass and draw 2 arcs as I just explained. So in either ways, your objective is just to locate point C, which should be located somewhere here. And then you're gonna connect this point C to point P to end up with the link BC in this way. So this is gonna give us the link BC. Then simply if we connected point C to point O4, we're gonna end up with the other link, which is the link number 4. And this is gonna be point C and B, and this definitely is gonna be point O4. Then your objective is just over this mechanism, your objective is just to locate or identify the G points, which is G2, which is already considered to point O2. Then your objective is just to find the location of point G3 over this link number 3. As he gave us the distance between BG3 by 50 millimeters. So your objective is just to measure 5 centimeters over the BC length from point CB. You're gonna measure 5 centimeters to locate point G3. So this is gonna give us point G3 in this way. Then you're gonna do the same. The distance from O4 G4 is already given to us by 25 millimeters, so 2.5 centimeters from point O4. You're gonna end up with point G4. This is gonna give us point G4 in this way. It makes sense? So we already located or generated the mechanism to scale, and we have to generate it to scale because we're gonna need it, we're gonna use it. Then the next step over the same mechanism, you are going to identify the direction of the acceleration EG for AG1, AG2, AG3, and all these center of gravity points. These center points, you're gonna draw the direction of the angle of the acceleration as already given to us. So the acceleration AG0, AG2, it should be 0. It has 0 acceleration because it is considered to a fixed point. But AG3, its direction was given, the angle was given by 312 degrees. So how we can identify the direction of AG3? Your objective is just to draw a line. What you're gonna do, you're just gonna draw from this point G3, you're just gonna draw a very light horizontal line. From G3, you're just gonna draw a horizontal line. So just let me double check the location of point G3. It should be here, right? So it should be this point. It should be the G3 point. So from this point, what I'm gonna do, I'm just gonna draw a line, very light line, horizontal line, in this way, and starting from this line I'm gonna use the protractor to measure the angle. So I'm just gonna draw a light line in this way over point G3, then I'm gonna take this line as a reference, and then I'm gonna measure the angle, which is 312 degrees, starting from the positive x. Assume that this is positive x, so your objective is just to rotate. As long as the angle is positive, we're gonna rotate counterclockwise. So it means that you have to rotate all the way till the 300. This is gonna give us the direction of AG3. This should be the direction of AG3, but we have to measure this angle accurately. So if you do have the, if you subtracted 360, the angle 360 negative 312, this is gonna give us 48 degrees. It means that the 312 angle, it is equivalent to negative 48. If it is negative, you can start from the positive x and rotate in the clockwise direction as long as it is negative. So this is equivalent to the negative 48, and this is how we're gonna measure this angle. So what you're gonna do, starting from this horizontal axis on the right, this right horizontal axis, this is gonna be your reference. Your objective is just to measure an angle starting from this axis and going this direction with 48 degrees, which is the difference of the 360 negative 312. You're gonna use the protractor and measure the angle, then you're gonna mark a point. This is gonna give us a point here. Then your objective is just to connect this point to point G to end up with the direction of EG, the acceleration EG3. Then over this line, you're just gonna draw the acceleration vector, which is gonna be the A3, AG3 is gonna be this one. This is AG3. Make sense? Then you're gonna repeat the same thing for AG4. AG4, its angular is negative 52. It means that from the G4 point, your objective is just to draw again a horizontal line the same way. Draw a horizontal line from this point this way. This line is gonna be our reference. Then from this line, we're gonna measure an angle of negative 52. It means that you're gonna go down with 52 degrees. You're gonna use the protractor and measure the angle. This is gonna give us a point somewhere here. Then if you connect this point to this point, you're gonna end up with the direction of the AG. Then you're gonna draw the acceleration EG as already given here in this direction. This is gonna give us AG4. Make sense? So the first step is just to draw the mechanism to scale. The second step is just to identify the centers of all these different members. Then at these centers, you're gonna measure the angles and identify the direction of the acceleration. How long is the arrow, the length of this arrow doesn't matter. The objective is just to locate the direction of these acceleration vectors, as already given to us for the given problem. Make sense? Then the next step is just to draw opposite to the acceleration direction, the inertia force that you calculated. We calculate for every link. We calculated inertia force and torque. Your objective is just to identify the direction of the torque and the direction of the force over the link. So for the link number 2, if you remember from the calculation, we got the inertia force and the torque for link 2 are zeros. So there is nothing that we're gonna do for link 2. We're gonna skip link 2. Moving to link number 3, we got the inertia force for the link by 47 Newton, but we have no clue about its direction. Its direction automatically it should be opposite to the acceleration according to the D'Alembert method that we just explained. So your objective is at point G3 is to draw, at point G3, you're gonna draw a line that is going opposite to the direction of the acceleration EG3. This is gonna give us the Fi3, which is the inertia force that we just calculated before. Fi3 in this way. Make sense? So this is gonna give us the Fi3 direction. How about the torque? The torque, it is already, we got it by the 0.208 Newton times meter. This is the torque value, but its direction, it should be opposite to the direction of alpha 3. So what is the direction of alphas? One of the things also that you have to identify the direction of the angular accelerations over the lengths. as long as the link is rotating. Like link 2, it rotates, but with constant velocity, so that's why its alpha 2 was 0. But alpha 3 was given to us, and the direction of alpha 3 was identified to be counterclockwise, and alpha 4 was given but in clockwise direction. So your objective is just to identify, just next to the link here, identify the direction. This is the direction of alpha 3, and alpha 4, it should be clockwise direction. It means that this is going to be the direction of alpha 4. So there should be a torque. The torque direction, it should be opposite to the alpha direction. So alpha 3 going up, this torque is going to rotate in the opposite direction. This is going to give us the Ti3, the inertia torque for the link number 3. Then we're going to have here another inertia torque for link number 4. This, it should be opposite to the alpha 4. So it should be in this direction. This is going to give us the Ti4. Make sense? How about the inertia force over the link? It should be opposite to the acceleration direction. So you're just gonna draw the inertia force going opposite to the acceleration Fi4 as already given here. Make sense? So this is the third step. Then the next step is just to try. If there is any external force, you're gonna add it to the mechanism. Do I have any external force in this given mechanism? There is nothing. There is no external force already given over the link 3 or link 4 or even link 2. There is nothing already given in terms of the external forces. It means that these are all the forces that should be considered when we're gonna do analysis for the mechanism. Then what? The next step is just to try to combine the inertia torque and the inertia force together in one equivalent force. Very similar to the general member case that we explained over the previous video. How we can do so? We're gonna follow the same procedure. So that's why we calculated for any link that has force and torque, we calculated an edge value. So what you're gonna do from the G3 point, or from the point that you have the force here, which is Fi3, your objective is just to draw a line that is perpendicular to this force direction, very light line. So I'm gonna draw a line here. This way, this line is gonna be, let me use this color. So I'm just from point G3, I'm just gonna draw a very light line this way that is normal to the force Fi3 passing over the point G3, which is the point of intersection of the force to the link. Then over this link, over this line, you're gonna measure H value that we calculated for number 3, for link number 3, we got it by 4.4 millimeter. And remember that we're already working as a scale 1:1. This is the scale that we already use for this graph. It means that the 4.4 millimeter will be drawn as 4.4 millimeter. So your objective is just to measure, starting from point G3, measure either up 4.4 millimeter or down 4.4 millimeter. Going up or down because we have to draw another from this point. If we're gonna move down, for example, we're gonna draw another point, another line that is parallel to Fi3, and this line, it should provide or produce a torque or a moment about this point G3 that it should be in the same direction of the inertia torque Ti3. So to have a torque that goes in the same direction of Ti3 or a force, this force, it should be going out. We have to measure the 4.4 down. So if we measure 4.4, and this is what you're gonna do, you're just gonna measure 4.4 and mark a point. Then from this little small point, you're just gonna draw another line, very light line in this way. This should give us the direction, this line should give us the new force, that it should be parallel to the original inertia force that is going to replace both the forces. And this is what we're gonna do. So we're gonna draw here from this point, we're gonna draw a line in this way. This is gonna give us the new force, the new Fi3. This is the new inertia force. And for this case, we can cancel this force and we can cancel this torque as well. So we can cancel the force and the torque. So we combine both of them into this new force Fi3, which is the brown one. Make sense? And this point, as you can see, this point is gonna be the point of intersection of this force to the link number 3. This point we're gonna need it for the analysis next. Then you're gonna repeat the procedure for the other link. For link 2, there is no inertia force, there is no torque. For link 4, we do have inertia torque and inertia force, so we have to combine them. But how about if we have just inertia force, or we just have torque, there is no need to combine them. If it is just one component, one thing, so that's it, we can move on. But if it is more than one thing in the middle, acting like one more torque or more than one force or torque, we have to combine all of these things together into one resultant force, as we did for link number 3. So now link number 3 is subjected to only one force, which is the new Fi3. This Fi3 is the original one, and the Ti3, we won't gonna consider them. Now we just represented them, then we came up with a new force and forgot about these two components of forces or loading for the next steps. Then we're gonna do the same for link number 4. For link number 4, we're just gonna draw a line that is normal to the Fi4. We're gonna draw a line that is normal to the Fi4 in this way. Over this line, we're gonna measure because H4 we got it by 9.1 millimeter. So we're gonna measure 9.1 millimeter either to the top or up or down. Which direction, right or left of the Fi4? This depends on the direction of the torque Ti4. To generate the torque in the same direction of Ti4, we have to pick a point on the top here, because we're gonna draw a force. We're gonna measure the 9.1 millimeter and mark a point, and from this point we're gonna draw a line. This line, it should be parallel to the original force Fi4 that we drawn before. This is gonna be the new force that we're gonna consider, and this is gonna give us the Fi4 force. Make sense? This is gonna give us the new Fi4 force, and we have to locate the point of intersection of this new force to the link number 4, because we're gonna need it. Then we can cancel this force and we can cancel this torque as well. So we're just gonna end up with one force acting on the link number 4, as already given here. Make sense? So this is for the first step, or the first thing that we're gonna draw to scale in the graph. Just generate the mechanism and locate the direction of the acceleration components, the angular acceleration and the linear acceleration of the center of gravity points. Then we're gonna identify the direction of the torque and the inertia forces. Then we're gonna combine them in one component over the same graph. Make sense? Till the moment we didn't do any force analysis. Make sense? Then we're gonna move to the next step. The next step is just to apply the superposition analysis method to do analysis for the different elements. For the superposition method, as you can see, after we combine all of these torques and forces together, we end up that the mechanism is subjected into two forces only. One force, which is the new Fi3 acting on link number 3, and there is another force acting or affecting on the link number 4. So initially we're gonna do analysis to the entire mechanism, to all of the mechanism, in case considering that there is a force. There is only one force acting with the mechanism, which is Fi3. Then we're gonna repeat again for the case that we're gonna consider that the mechanism is subjected only to the Fi4. Then we're gonna get results from the first case and the second case, then we're gonna combine them. Make sense? So there is still, in terms of the graph, there is still like 3 more things that we have to do to finish the force analysis of this mechanism. Make sense? So now we're gonna do force analysis of the mechanism. We're gonna start the force analysis. This is gonna be the second step in the general procedure that we considered here. So we're gonna do the force analysis using the superposition principle. Okay. So for the superposition, just let me remind you with the mechanism. The mechanism that we already generated, it was like in this form. Like we do have this at the 4-bar linkage, very quick. Like this is like a rough or a tentative shape of the mechanism. And we do have here 2 forces. We agreed that we should have 2 forces. One force, which is the Fi3, and there is another force, which is the Fi4. These are the two forces that are already acting on the mechanism. So if we decided to work on the superposition approach, we're gonna break it down into like two separate problems. In the initial case, we're gonna consider the mechanism in this way under the influence of only one force, and this is the mechanism in the second case, under the influence of another force. So this is gonna be the mechanism under this Fi3, and this is gonna be the mechanism but under the Fi4, right? Like these are the two forces that we already have. So let us work first, do the force analysis due to, we're gonna start here with due to the Fi3 only. We're just gonna consider the first case that, and for this case, it means that the Fi4, we're just gonna assume it is like 0 initially for this case. Then we're gonna do analysis for the entire mechanism, like you're already working over a separate problem. Then we're gonna repeat for the second case. Make sense? So if we decided to work, we do have link 2, this should be link 2, link 3, and link 4, right? So if we decided to work over this problem, so if I ask you how many forces acting over link 2, starting with link 2. Link 2, if I ask you how many forces, there should be one force here and there should be another force here, right? So it should be like two force member. There is nothing else really acting over this link. But remember that in the description of the problem on the top, he required the torque that needed, that should be acting over the crank to give rotation or motion to this mechanism. He requested for the torque. So what does it mean? It means that this member, number 2, it should be subjected to a torque. And that's why it is required. So originally, this member, number 2, there should be another torque here acting over this link. Like there is a torque acting over link number 2, and this torque initially we're just gonna neglect this thing. We're just gonna work over the force analysis through link number 3 and 4, and then we're gonna keep this one till the end to find this torque. This is the torque that is already required. So originally link 2, it should be two force and couple link. The type of this link number 2, it should be link 2. It is two force and couple member. But remember that this link 2, we're just gonna skip this one till the end. We're gonna do nothing. We're gonna do nothing for link 2 till the end of the problem, once we finish all the two cases, even once we finish this case and the second case. But now, so now let us move to link number 3. Link number 3, how many forces acting over this link? This link is gonna be 3 force member. Why 3 force member? Because there is one force at this point B, because this is point B and this is point C, right? So there should be one force at point B. There should be another force at point C, in addition to the middle force in the middle. So this is gonna be 3 force member. This is gonna be 3 force member, and to do analysis, force analysis to this member, you're gonna apply the same approach that we explained over the previous video for the 3 force member. Make sense? Now let us move to the link number 4. For link 4, how many forces acting over this link? Only 2 forces. One force at this point O4 and another force at point C, and nothing else. So it is simply 2 force member, and we said that for the 2 force member, there is no need to do any analysis, or there is no need to draw any force polygon. So given this information, we said that we're gonna skip the first link. We're gonna skip this one, the link 2, I'm sorry. We're gonna skip this one till the end. So we have to work over link 3, and we're gonna work over link 4. Link 3, it is 3 force members, so there should be force polygon should be drawn for this link, but there is no need to draw any force polygon for the 2 force member. And something that you should understand about the 2 force member, like the 2 forces are parallel, and they should be considered to the line that connect the 2 ends of the link together. So we're gonna take use of this data and try to do analysis for the mechanism in the case that it is subjected only to the Fi3, which is this force. Make sense? So now I'm gonna move to the drawing sheet. Then we're gonna work on the analysis due to the Fi3, assuming that the Fi4 is 0. Then once we finish this one, we're gonna repeat again for the second case. Make sense? So now in the drawing sheet, I'm just gonna specify a region or an area like part of this drawing sheet. I'm gonna specify this area to start generating the things for the analysis of the mechanism due to Fi3. So I'm just gonna type here due to Fi3. And this is gonna be the first scenario or the first case. Make sense? So your objective basically is just to have a copy of the link number 3 and link number 4. We agreed that we're gonna skip number 2 till the end of the problem, right? So we're just gonna have a copy of link 3 and link 4. Here, you should keep in mind that you have a copy that is completely parallel with the same lengths of link BC and link O4C, but make them separate. So starting with the link BC, I'm just gonna draw a line that is, make sure that this line is completely parallel. And you're gonna measure over this line. You're just gonna draw a line and measure over this line the distance from any point, starting from this point, for example, as point B. You're gonna start from this point, assuming that this is point B. Then you're gonna go all the way to measure up to point C. This is gonna give us the link number 3. And mark this, this is point B, and this definitely is gonna give us point C. And do the same, have a copy of the link number 4. You're gonna draw a line that is completely parallel. Starting from this point, assume that this is like point 0.04. Then you're gonna go parallel to the link number 4 and measure the distance to specify the other point, which is point C. So this definitely is gonna be point C, and this is gonna be point 0.04. Make sense? Simply, you're just gonna have a copy of each one of these two lengths. All right. Then what? Your objective is just to identify any forces acting on this link, assuming that Fi3 is with a value, but Fi4 is already 0. Fi4 is already 0, so there is no forces acting over this link except the other forces. There should be one force here and should be another force there, right? And how about this link? There should be a force, which is Fi3, that already acting in the middle at this point. So that's why it was important to identify this point, which is the point of intersection of this Fi3 to the link number 3. Once you locate this point, you're gonna measure the distance from B to this point or C to this point. How you can find this distance? You can simply find this distance. There is no need to measure it. You can use the compass and fix with the metal tip here, and touch with the lead tip. You're gonna end up with this distance. Then you're gonna move with the same opening of the compass. You're gonna move to this point, fix with the metal tip here. Then you're gonna cut an arc here to locate this point of intersection. Remember that this point, it is not point G3. It's different. It had been shifted with H. So your objective is just to locate this point over the link. It's gonna be this point. Then from this point, you're gonna draw a line that is completely parallel to the line, to the force Fi3. This is gonna be the direction or the force Fi3 as we specified up there. So this is gonna give us the Fi3 force. Fi3, which we already got it by 74 Newton, if you remember from the calculations. Make sense? So we got this force. Just let me do it like more accurate. It's gonna be this one. And this is the direction of the force Fi3 equals 47 Newton. Make sense? So this is for link 3 and this is for link 4. Then what? We have to work over these reaction forces. What should be the force here at point B? This force, it is this. Remember that these are the links. This is link number 2. This is link 2, right? This is link number, put it in a circle. This is link number 3, and this is link number 4 somewhere, right? So it means that this should be link 4, and this should be link number 3, right? So this point B is common between link 2 and link 3. So this force at link 2, it should be F2, 3, but we're gonna give it dash because this is the first case. This F23, we have no clue about it. How much is its direction? Do we have its magnitude? Do we know what is its direction? We have no clue. So it is fully unknown. So that's why we put this curved thing. Then how about buoyancy? Buoyancy is a common point between the link number 3 and link number 4. So this buoyancy that belongs to the number 3, there should be a force here that comes from 4 acting on 3, right? So it is 4, 3, F43 dash. But the same thing for this link, we have no clue how much is the magnitude of F43 or the direction of F43, we have no clue how much it is. This is for the link number 3. Now let us move to link number 2. What is the type of link number 2? As we explained on the top there, it is two-forced member. So what should be the force at buoyancy? The force at buoyancy should be the force F34, which comes from 3, 4. And you should understand that the F34, it should equal to the F43 dash and with parallel to each other but two opposite directions. Make sense? So there should be a force here at C, and there should be another force here. This force, it should be the F14, the force that comes from 1, which is the ground, because the ground there is link number 1, right? So it should come from 1 acting to 4. And what is the thing that distinguish or characterize these two forces together? These two forces are belonging to a link, to a two-force member. Two-force member, it means that the two forces acting on the link, they should be opposite to each other, parallel to each other, and having the same magnitude, and their line of action, it should be coincident to the line that connect the two ends of the link together. If we decided to connect this point to this point, we're going to end up with the same line of the link. It means this indicates as long as this link, it is a two-force member, it means that the correct direction of F14 and the correct direction of F34, it should be parallel to the line. So this is going to give us the direction of this force and the direction of this force. This is for link 4. But how about the direction of these two forces? Are they already tension or compression? We have no clue. We're just gonna draw lines, then we're gonna specify. We don't care. We said that if we just draw lines, it means that, or we knew their line of action, this like it is given direction. It means that the direction it is like given. So since this FR3, it should be parallel to the F43, it means that the direction of this force is given. So simply we can draw from this point C a force going in this direction. This line is going to give us the direction of the force F43. It means that its direction is already given. And remember that there is no need to draw any force polygon to the link number 4. Why? It is two-force member and nothing that we can do more than what we did for this link. Now we have to work over link number 3. Link number 3 is a three-force member. We can do a force analysis for this three-force member under only one condition, in case that we have 3 information, 3 things already given to us, and we are seeking 3 other things. So as you can see, this force, inertia force in the middle, it is fully defined. This force has a known magnitude, but we don't have its direction now. We got its direction from force 4, from link 4. But this one is fully unknown. So we don't have 3 unknowns only. So we can do analysis to this link. But before that, initially when this one was unknown, we cannot do any force analysis to the link unless we specify the direction of this force first. How did we specify the direction of this force? We got it from this link 4. This link 4 is a two-force member, and from this condition we understood that this force, it should be considered to the line of action between, or the line that connects these 2 points together, and definitely this force, it should be parallel to this one, so we got the direction of F43 dash. Now we can do force analysis to this mechanism. How? Apply the procedure that we explained before in the previous video. So we're gonna start from a 0 point. This is gonna be the O, assume that this is the OF, the 0 point of the force mechanism. Then initially you're just gonna draw the first inertia force, the first fully defined force. The first defined force is this force, which is 47 Newton. So I can assume scale 1 to 1. To draw this one. So what I'm gonna do, I'm just gonna draw a line that is completely parallel to this force in this direction. Then over this line, starting from O4, from OF, I'm gonna draw this line, and over this line I'm gonna measure the distance, which is already given to us by 70 by 47. So I'm gonna use different color just to distinguish things here. So this is gonna be the force polygon for this one. Starting from this O4, I'm just gonna draw a line, and the length of this line, it should be this way. So this is gonna give us the first line, and mark a point. This is gonna be the end, and this force definitely is gonna be the Fi3. Then from one end you're gonna draw one force, from the other end you're gonna draw the second force, right? So one of the forces that we already have its direction is the F43. The F43 already have its direction. So simply from one end, let us assume that we're gonna draw it from this end. We're gonna draw a line that is parallel to this F43. So from this point, I'm just gonna draw a line that is parallel to the F43. This is gonna give us a locus to another point. But we need from the other point to draw a line that is parallel to the F23. What is the direction of the F23? How we can find it? Your objective is just to extend the two forces that their directions already given or already known. You're gonna extend this force. And then you're gonna extend the second force. Extend this direction this way. So they're gonna meet together at a point. If we try to connect this point to this point B, to point B, this is gonna give us the direction of the force F23. So we got the direction of F23. We're gonna use this direction, and from this point, we're gonna draw a line. Let us use the same color here. We're gonna draw a line parallel to the F4. To the F23. From point O2, from the other point, we're gonna draw a line that is parallel this way. So these two lines, they're gonna intersect at a point. Then we can simply come up with the force diagram as already given here. So this is gonna give us this line. We can go over this line. This is gonna give us the first force component, and this is gonna give us the second force component, and this is gonna give us the third force component. If I3 already have its direction is going up, and since if I3 going up, all the three forces should move in the same direction. So this is gonna give us the direction of the F23, and this is gonna give us the direction of the F23 dash. This is gonna be the F23 force, and this is gonna be the F43 dash, and should be dash. Make sense? So this is the force polygon, and we got it. So we finished for this one. Your objective is just to measure the distance between this point and this point to come up with the value of F23. And remember that we are using scale. The scale here, it is 1 to 1 for this force polygon. It means that you're just gonna measure this distance directly. This is gonna give us the force F23 dash. The same thing, the magnitude of the force F43 dash. But let us specify the directions over the drawing. So we got the direction of the F43 dash in this direction, right? F23, this is the direction of F23 dash, and we got the direction, this is gonna be the direction of the F43 dash as we already got it. Make sense? Now we're gonna move and we're gonna measure, as we mentioned, we're just gonna measure this F23 dash and the F43 dash, these distances. This is gonna give us the force of these two components. And definitely you should understand that the F3 dash, F34 dash, and the F14 dash, they are equal to the F43 dash. Mean that this force equal to this one in terms of magnitude, but this force is different. Because in this drawing we do have four forces, F23, F43, F34, and F14. Make sense? So we're gonna go up here. For this part, then we're gonna say that from the force polygon, from the force polygon, we got this data. We got the magnitude we can calculate. We calculated or we measured the magnitude of F23 dash, which should equal to the magnitude of F32 dash, because this force we're gonna need it for the analysis of the of link number 2, it should equal to the 36. We measured this value by 36 millimeters. We got it with 36 Newton. And the same thing, the magnitude of the F43 dash, which should equal to the magnitude of the F34 dash, and in the meanwhile equals to the F14 dash. And remember that this dash, it stands for the first scenario, for the first case. Then in the second case, we're gonna have double dash. This is gonna give us the 20 Newton. We got this value by the 20 Newton. Make sense? So we finished the first part. We finished the first case. Now we're gonna move to the second case. We're gonna repeat the same procedure, but for this case, we're gonna assume that Fi3 is 0, but Fi4 as already we calculated by the 30 Newton. Make sense? So now let us move to the second scenario, the second case. So in the second case here, we're gonna work due to Fi4. It means that we're just gonna assume that Fi3 equals 0. This is gonna be the second case. So if we did so, how about we said that we're gonna skip link 2 till the end. How about link 3 for this scenario? For this case, link 2 is gonna be 2 forced member, right? You're just gonna have one force at this end and another force at this end, and that's it for link number 3. But link number 4 will be 3 forced member. Agree? So link 2 definitely is gonna be link 3, I'm sorry. Link number 3. Link 3 will be 2 force member. Mean that there is no force polygon that is going to be drawn for this link, but link 4 will be definitely 3 force member, and we're gonna have a force polygon for this member, right? So then we're gonna go to the drawing sheet again, as we used to do for the drawing sheet, and now we're gonna work over the second part. So what I'm gonna do, I'm just gonna draw a line just to separate this one from this one. This is like we just gonna put here a separate line in this way. Then we're gonna work due to, we're gonna say that this is the part is due to Fi4 in this way. Make sense? Then what your objective is just to copy again the two links, link 3 and link 4 as we did before. Typically just copy them. Make sense? So what I'm gonna do, I'm just gonna have a copy of these two links. So this is the link number 3 with the same scale as we did before. This is gonna give us link 3, and this definitely is gonna give us link 4. In this way. So in such a way that this is point C, this is gonna be point 04, and this definitely is gonna be point C, this is gonna be point B. Make sense? Then what? For the link number 3, just 2 force members. So skip this one till the end and just specify the direction and draw the force Fi4. The force Fi4 is already acting at this point. So you have to measure this point as we did for this point for the Fi3. So you'd have either two options. You can fix with the metal tip here of the clamps and fix with the lead tip here and pick this distance and fix here and draw an arc to end up with the location of this point. Or you can measure from point C, it's up to you. Or you can use measurements, it's up to you. So I'm just gonna look at this point, we got it here. Then your objective is just to draw a line that is completely parallel to the original Fi4 that already drawn on the top. So we're gonna draw a line that is completely parallel in this way. This definitely, it should give us the direction of Fi4 as already given on the top. Make sense? This is the direction of the force is already going up. Then what? This force is 2 force member. We agreed that any 2 force member, that the 2 forces acting on this member, they should be parallel and they should be considered to each other, considered to the line that connect the two ends of the link together. So it means that we should have one force acting at point B. It should be parallel. These 2 forces, one force here, and there should be another force, and these 2 forces, they should be parallel. So this is the line of action of these 2 forces. What should be this force? This force, it should be the F2, 3 double dash, because this is the second case. This is the F2 because this is the force that comes from link 2. B is common between link 2 and link 3. So this is the force that comes from link 2 acting on link 3. What is the direction of this force? Is it this direction or the opposite direction? We have no clue. But this is the line of action of the force. To us, it is like given direction. The same thing for the other link. This force, which is point C, is common between link 3 and 4. But this force is acting over link 3. This is link 3. But this one is link 4, right? So this force, it should be the F that comes from 4 acting on 3 double dash. This force, it should be parallel considering to the link itself or the line of action or the line that connect the 2 points, point B and C. Make sense? How about this force? At this point C, there should be another force which is F34 and F34 double dash. It should be completely parallel to this force. So what does it mean? It means that we do have one direction here of this force. At point C, we do have this force. This is the direction of the force at point C. This force, it should be the F34 double dash. Make sense? Just let me write this F34 double dash. This is one force. How about the force at the point O4? This force, it should be the F14 double dash, and we have no clue about this force. We don't have its direction. We don't have any magnitude for this force. So as you can see, the link 4, it is 3 force member, and it has 3 unknowns. The magnitude and direction of F14 and the magnitude of F34. So we can do analysis for this link, but there is no need to do any analysis for the 2 force member. It means that we're gonna draw only one force diagram for this link number 4. Starting from any point to be the 0 point. So I'm gonna assume that this is the 0 point, OF. This is the original point. Then from this point, you're gonna start the drawing by the Fi4, which is the fully defined force. And remember that the Fr4, it is given by 30 Newton. So what you're gonna do, we get 30 Newton, it means that the scale 1 to 1 is enough. So I'm gonna draw a line parallel to this F14 with a length 30 millimeters. So from this point O4, I'm just gonna mark a point and draw a line with a length 3 centimeters, which is equivalent to 30 millimeters. The end of this line should give us the force F. This force, it should be the Fi4. Make sense? Then you're gonna draw one line from one end and another line from the other end. But we have to specify the directions of the forces. Can we specify the direction of F14? Yes, if we extended this force and extended the F14, Fi4, both they're gonna intersect in a point. Connect this point to this point, you're gonna end up with the direction of F14 as we did before for the previous case, right? So our objective now is just to connect or extend these 2 forces. I'm just gonna extend this force with a line and extend this force with a line. These 2 lines, they're gonna intersect it together in a point. From this point, I'm just gonna connect this point to the point O4. This way, this is gonna give us the direction of the force. So this green line, this is the direction of the force F14. Then from one end, you're gonna draw a line parallel to the F14, and from the other end, you're gonna draw a force that is parallel to the F34. So let us assume that we're gonna draw a line from the start point parallel to the F14. This is gonna give us this line. And from the other point, we're gonna draw a line that is parallel to the F34. From the other end of the Fi4 that we draw. So these 2 lines, they're gonna intersect together in a point. This definitely gonna give us gonna close the force polygon to end up with the F14. This is the line for the F14, and this line is gonna be for the F34. Make sense? And what are the directions? So this should be the F14 double dash, and this should be the F34 double dash. What should be the directions of these forces? All the forces should be rotating in the same direction. So we're gonna have Fi4, then we're gonna have F34, then we're gonna have the F14. All of them, they should be rotating in the same direction. Then if we measure the F14 distance and the F34 distance, we're gonna end up with their values, as we did before. But before we identify the values, specify the directions of the forces. So the F34, it should be directed up. So it should be directed up. It should be going up in this way. And the F3-4 in response, it should be going down in the opposite direction to this one, and definitely the F2-3 should be opposite to this force. These two forces, it means that length 3 is going to be compressed for this case. And we forgot to specify the directions, by the way, of the F1-4. This force, it should be going up, here it should be going down, opposite to this one. It means that length 4, due to this Fi3, will be stretched or subjected to tension, but this length number 3 will be compressed, subjected to compression because of the Fi4 acting on length number 4. Make sense? And how about the direction of the force F14? F14, it should be going down. F14, we got it that it goes down in this direction, so this should be the direction of the F14. Make sense? Now we're gonna measure this distance F14 and the F34, and we're gonna define their values here on the top. So we're gonna say that from here, from the force polygon, we got the magnitude of the F34 double dash, which should equal to the magnitude of the F43 double dash, equals, we got it by the 17 Newton from the measurement, and the magnitude of the F23 double dash, which should equal to the magnitude to the F32 double dash, equals to the 17 Newton as well. So we got them equivalent, and we do have the magnitude of the force F14 double dash, we got it by the 29 Newton. So these are the forces that we already got it for the second case. So this is the concept of the superposition, that we consider the two scenarios. We consider the two cases. The first case, and we got these forces, the same forces, we got them back again, but using the second case. Now we do have F23 dash and we do have F23 double dash. So we have to combine them. We have to find the resultant of all of these different forces. So for example, for this mechanism, either at point B, there should be some forces here. This force, which is F23 or F32, how much it is? This total force, it should be the F23 dash plus the F32 double dash, F2 dash plus the F23 double dash that we just got them from the superposition analysis method. Make sense? So we have to find the resultant of all of these different forces, and this is what we're gonna do here. We're gonna draw different force polygon. Remember that we should have how many reaction forces that we are seeking. We seek one reaction force at point B, we seek another reaction force at point C, and reaction force at point O4. These are the three reaction forces that we already got. But how about the reaction force at point O2? We aren't gonna get this one unless we do analysis to link number 2. We skipped working over link number 2. So that's why we weren't gonna able to find this reaction force at this instant of time, but we're gonna find it once we're gonna work over link 2. Remember that we're skipping link 2 till the end. Why? Because it has a torque and we are seeking the value of this torque. So we have to do analysis for all the other links. Then we're gonna do the force analysis for the link number 2 at the end. So it means that we can find 3 reactions. The reaction at point B, the reaction at point C, and the reaction at point O4. To find these resultants, we have to draw 3 force polygons for the 3 reactions that we already got them. Starting with the F23, for example. So I'm just gonna try to confine the drawing into, try to keep like a space for the resultant. So I'm just gonna draw a line here, this line, then I'm gonna try to draw all within this small little area, I'm gonna try to generate the drawings for the resultants. So I'm gonna work here for the resultant forces. Your objective is just to try to combine the different forces that we found in one resultant force, right? How we can find the resultant? Your objective is just to draw one force, and from the end of the first force, you're gonna draw the second force, then the resultant is the one that should be closing the shape. Remember that finding the resultant is different than the force analysis. The force analysis you can draw, as we discussed in the previous video, we can draw one force from one end and the second force can be drawn from the second end, from the other end. But for the force analysis, for the force resultant, all the forces should be rotating in the same direction. You're gonna start with one force, from the end of this force you're gonna start the second one. Make sense? And this is what we're gonna do. Now let us work, for example, start with the F2. For the F2, we do have F2 dash, this is the direction of the F2 dash force, and we got F2 3 double dash, this is the F2 3 dash, and the F2 3 double dash, this is the direction of this force. And remember that the F3 2 3 double dash, this is its direction and its value, which is the 17 Newton that we already got before, which it should be equivalent, or it should be equal to this value. So if we decided, we already got before the F2 3 dash, we got it 36 Newton, and we got the F2 3 double dash, we got it 17 Newton. So let us assume scale 1 to 1 and start from any 0 point. Let us start from this point. At the 0 point, then what I'm gonna do, I'm just gonna draw a line parallel to the F2 dash, parallel to this force, and going in the same direction. I'm gonna start, or assume that we start from this point. So I'm gonna go down, I'm just gonna draw a line and measure over this line the value of the F23. The F23 dash, we got it by 36. So it means Newton, it means that assuming scale 1 to 1, so I'm just gonna assume that this is like 36 millimeter. Then from the end, this is gonna give me the F23 dash. From the end of this force, from this point, I'm just gonna draw another force that should be parallel to the F23 double dash. F23 double dash is going up, it goes up. So I'm just gonna draw a line that going up, and the magnitude of this force, we got it by 17 Newton. So its value according to the scale is gonna be 17 millimeter. So I'm just gonna measure 17 millimeter and mark a point. This is gonna be the end of the F23 double dash. So I do have F23 dash going in this direction, F23 double dash. The resultant one, it should be closing the triangular shape. So your objective is just to connect this end point with the start point. If we connected them, we're gonna end up with the F2 force. This is the resultant F23 force. So this is the total F23 force. So we got one reaction force, one resultant one. We still have two, the F14 and the F34 or 43. It doesn't matter, because F34 or F43 both are equal with the same magnitude but two opposite directions. So let us work over the F43. The F43 dash, we got its direction. This is the F343 dash. We got, this is its direction. It goes down, right? And we got its value from the analysis of the first case. We got it by 20 Newton. Make sense? We got it by the 20 Newton. So what does it mean? Starting from any point, assume that this is the 0 point. This is the OF. And we're gonna draw a line that is parallel to the F43 dash. It means that it goes down. And over this line, we're just gonna measure a length of 20, which is the value 20 Newton. It means that it's gonna be 20 millimeter. This is gonna give us the F43 dash. Then from the end of this point, from its end, you have to continue drawing, going down. With the F43, which is this one. F43 double dash, it goes down in this direction. So from this point, you're gonna draw a line going down, and the value of this force, we got it by 17. So you're gonna measure 17 and mark a point. This is gonna give us the F43 double dash. Then you just gonna close the shape. In this way, this is gonna give us the total force. Remember the directions, like F43 dash, F43 double dash. The F43 should be on the opposite direction. If we're already following the same direction, this one, it should go up. No, but instead this force, it should be going down because it is resultant. So it's gonna be F43, this is the resultant force. Then you can measure this value. This is gonna give us the total F43, how much it is. The same thing, we can measure this force of the F23. We can end up with the value of the F23. We still have one more, which is the F14 force. F14, we do have F14 double dash, and we do have the F14. Both are going down. As you can see, both are going down. So we're gonna start from any point. Assume that we're gonna start from this point on the top. Then you're just gonna measure a distance. Draw a line parallel to the F1 dash. Or you can start with the F1 double dash, either one. So start, for example, with the F1 double dash. I'm just gonna draw a line parallel to the F1 double dash, F14 double dash from this point OF. Draw a line. Then over this line, the length of one F14 double dash is 29 nanometer. So you're gonna measure 29 millimeter. Then from the end, you're gonna draw another line that is parallel to the F14 dash, which is this force, parallel to the F14 in this direction. And over this line, you're gonna measure, over this line, you're gonna measure a force, the force F14 dash, we got it by 20 Newton, so you're gonna measure 20 millimeter, then you're gonna close the triangular shape. So we're gonna end up with very narrow, very thin triangular shape, right? So once you got this force, so this force, a little force here, this would be F14 double dash, and this very small force here, it should be the F14 dash. Then the resultant force is the one that is going to close the shape. If we're already moving in this direction and going down, the F14, it should be closing the shape. It should be on the opposite and moving in the opposite direction. So this direction, it should be the direction of the F14. Then you can measure it, you're going to end up with its magnitude. Make sense? So going back again here. So we already generated the resultant, and after we do the measurements, this is going to be the third step, the third thing. It's just to work over the resultants. It's just to find the resultant traction forces. So for number 3, just to work over the resultants. Find resultant forces. Or the total actions as already required. So you should understand that the magnitude of F14, it should equal to the magnitude of F41 that we already got it from the measurement by 49 Newton. This is one force, one action force. Also another action force, which is the F34, its magnitude, it should equal to the F43 force. Both they should have the same magnitude. We got it by 31.5 Newton. This is another action force. The third one is the F23, the magnitude of this force, and should equal to the F32. We got it by the 50 Newton from the measurement, approximately. Make sense? So we done everything for this mechanism. We still have only one thing left, which is the length to find its torque. This is the last requirement. Make sense? So number 4 is gonna be the length, the crank. We're gonna work over crank number 2 that we skipped at the end, right? This crank, it should be 2 force and couple member, as we discussed before, right? Why? Because this crank is gonna be like, this is the crank number 2. So this is the crank. There should be one reaction force here, and there should be another action force here. What should be this force? This force, it should be the F12. This is the force that comes from the ground, 1 acting over 2. And this force, it should be the force that comes from 3 acting over 2. That we already got it. We got the magnitude of F32 by 50 Newton. And the direction of this force, it should be opposite to the F23. What is the direction to the F23? This is the F23 direction. This is the resultant force that we got. And its direction, it should be going down here. So we can find, so we do have everything regarding this force. This force, it should be going up. Because the F23, remember, down, it is already going down. F23 is going down. So the F32, it should be parallel to this force with the same magnitude but opposite direction. So if this is the direction of F32, and this should be, there should be a torque here. There should be a torque acting over this length. We don't know the direction of this torque initially. It would be either this direction or this direction. But the thing that you should understand about the 2 force and couple member, that the two forces acting at the two ends, they should be parallel to each other, having the same magnitude. So what does it mean? It means that the magnitude of this force is also 50 newtons. So we have the value of this reaction, F12. We got it automatically. And what about its direction? It should be opposite to the F32 and parallel to it. Then what? If you try to draw a line that is normal to both of them, this line is gonna give us h, a height. We can measure this height as long as we're drawing this thing to scale to calculate the torque. This is the torque value. To calculate the torque acting over the crank. This torque, it should come up with kind of motor already fixed at the joint here to give rotation. This is like external torque, should be acting over the crank to give it rotation, to give movement to the mechanism. Make sense? So if I ask you what is the direction of the torque due to F32 and F12, both forces rotating in this direction, like F12 and F32, both are rotating in this direction. So this is the direction of the torque due to these two reaction forces. This direction, as already given here, it is counterclockwise direction. The torque that should be acting over the link, number 2, it should be opposite to this torque that due to the reactions. Because this torque that acting over the link, it is external torque. This is the torque needed to operate the system. It should be opposite all the time, opposite to the direction of the torque that would be produced because of the reaction forces acting on the crank. So you're just gonna ask yourself, what is the direction of the torque of F23 due to F32 and F12, these two reaction forces? This direction of the torque is gonna be clockwise direction. So automatically the external torque that we are seeking, its direction, it should be clockwise direction. So we got the direction, but we still need the value. How much is the value of this torque? As we explained before in the previous video, this torque, it should equal to one of these two reaction forces, either F32 times h or equals F12 times h. F12 or F32, this is just the magnitude value. We got them by 50, so we still need the value of h. This h is different than h3 and h4 that we calculated before. So how we can find this h? We have to draw this thing to scale. That's why we're gonna go back again to the drawing sheet. And next to the mechanism, I'm just gonna draw the link number 2, have a copy of the link number 2. Next to the mechanism here, starting from this point, assume that this point is O2, assume that this is point O2, then from this point I'm just gonna draw a line that is parallel to the link number 2, and the length of link number 2 was given as much as it was given. You're just gonna measure the distance, or you can get the distance or the length of the link 2 from the drawing, typically the same. Make sense? Then you're gonna mark the other point. This is gonna give us point B. Then what? Your objective is just to draw the direction of the force F32. We said that the direction of the force F32 should be opposite to the F23 force, but it should be parallel. So your objective is just to have copy of this parallel line of this force down here. You're just gonna have a parallel to this force on the top at point B. So at point B, you're just gonna draw a line. This line is gonna give us the direction of the force, which it should be the F32 force. And it should be going in this direction. So definitely the other force, which is F12 at point O2, it should be opposite to this force but parallel. So it's gonna be parallel but opposite in this way at point O2. And this definitely is gonna give us the direction of the F12 force. Make sense? Then from either point O2 or point B, you're gonna draw a line that is normal to the force, to the two forces. This is gonna give us the distance D or the distance H. Your objective is just to measure. Draw a line from this point. You're just gonna draw a line that is normal to both of them. This angle, it should be 90 degrees. Then you're just gonna measure this distance from this point to this point. This distance should be the h that we are talking about. You're just gonna measure this one and reverse the scale. Remember that we were using scale 1:1 for this graph, for this mechanism, right? So your objective is just to measure this h distance. From the measurement, we got this distance, we got this h. Then you're gonna go up here. From the measurement, we got h equals, we got h equals 17.5 millimeter. This is what we got from the measurement. So if you multiply this 17.5 millimeter, which is this value, times 50, 17.5, this is gonna give us the torque value by 875 Newton times meter. This is the torque needed to give rotation to the mechanism, or to give rotation to the crank. And as long as the crank is going to rotate, this is gonna give us directly a rotation to the link, and the direction of this one, it should be clockwise direction. This is the direction of the torque. So we're gonna say that there is a torque that should be acting over this link. This torque, it should be rotating in the clockwise direction. This is gonna be the T2, and that's it for this problem. So it is a long problem, lots of steps. So you have to practice this thing. But this is how we can do force analysis graphically for a mechanism like 4-bar linkage for the dynamic force analysis. So I have tried to move step by step, slowly, to explain to you every detail for this, to generate these drawing, and I hope that you understand these steps. Okay, so that's it for this mechanism. And this is, so in this video, just a very quick review of what we discussed here. We explain initially the general procedure of how we can do dynamic force analysis, then using the superposition, and we explain what does it mean, the superposition principle for this type of the force analysis. Then I give you an example with more details how we can do the calculations. We got all the reaction forces. These are the resultant reaction forces. In addition, we got the torque that was required from us, and these are the details of the drawing. Remember that you have to have all of these sketches and drawing in one A4 sheet, as I already generated here. So try to make use of the space as much as you can, because there are lots of drawing that should be generated over this drawing sheet. Make sense? So that's it for this video, and that's it for the force analysis part using the graphical method. All right, so thank you, and see you in another video.